of alcohols using copper, zinc, oxide, alumina, plus cerium and manganese catalysts. It is a contribution from Brunel University, University of Twente, and University of Limerick. The authors are Sla, Wallman, and Ross, and it will be presented by Professor Julian Ross.
Well, I can't offer you a limerick today, but I can offer you some archaeology, academic archaeology at that point, because this is work that was done when I was still in Twente, and it was summarized in a thesis which was published about 6 months before I left Twente. The front of the thesis actually has a photograph of a petrol pump, and I think it was actually taken in San Diego, or should I say it was a methanol pump. And some of this work was presented at a conference in San Diego by Joop Sla some years ago. This is a continuation of that work, and I'm concentrating here now on some work that he did on the effect of cerium and manganese additions to these catalysts. Well, I think I needn't pay too much attention to what's on this slide. The background to this work was that at the stage when we were doing it, there was an interest in producing higher alcohol mixtures with methanol because of the fact that when you try and make a blend of methanol with petroleum, you get phase separation unless there are significant higher alcohols present in the mixture. So what we were aiming at was this a mixture that was suitable for improvement of octane number. If large fractions of methanol and isobutanol are formed, then there's another possibility, and that's the production of MTBE from that mixture. And in fact, as we'll see, some of the catalysts that we've been looking at are quite selective for isobutanol synthesis. Now, most of the work that we did was done using as a starting point an existing copper zinc alumina catalyst. It was a BASF catalyst, but we made our own catalysts as well. In some cases we added the material by impregnation. Sometimes we made our own materials by co-precipitation, adding the other additives by co-precipitation during the preparation. What I want to do in this particular talk after my introduction is then to talk a little bit about the experimental, the method of preparing the catalysts, talk a little bit about the analytical techniques that we have used, the catalytic setup that we have used for the measurements, and then I'll say a little bit about the deactivation behavior of the catalyst in use, and particularly I'll concentrate on the selectivities and the analysis results. And then I'll say a little bit about the mechanism. It's highly speculative because we don't have direct evidence, as in our last talk, for mechanistic aspects. We must speculate based on very largely our product distributions. Now, two methods then that were used for the catalyst preparation. One was co-precipitation. The co-precipitation technique has the advantage that you form this intimate mixture between the copper, zinc, and aluminium and the other components. And as we will see, there is some evidence that at least in one of the combinations that the additive is very well dispersed throughout the bulk of the catalyst material. That in the case of cerium, there's a little bit more evidence for surface segregation, but with manganese that it's pretty well dispersed through the catalyst. By impregnation, we are obviously putting the additive on the outside of the catalyst surface, at least in the early stages. There will be some incorporation during the calcination stage, but we are tending to get a surface concentration of the additives. And what we were doing here was to try and see what the importance was of the surface concentrations. Now we've added various different quantities of the additives, anything between 0 and 8 mole percent of the manganese and cerium additives in these particular materials. I think this is fairly obvious. One has to analyze the catalysts after they've been made, so we use either atomic absorption spectroscopy or X-ray fluorescence to measure the additive concentrations and to check the composition of the catalyst that we started with. We've checked the phase composition with X-ray diffraction. Mostly one only sees the typical diffraction pattern of a traditional copper, zinc, alumina catalyst, but in some cases we do actually see a separate phase forming. We've also done some surface analysis, in inverted commas if you like, copper surface area using the method described by Chin, using N2O decomposition as a method of monitoring the copper area. There is some discussion about how fair it is to say that that's all surface copper, but it is a measure of the copper surface area. And we've done some X-ray photoelectron spectroscopy work to look at the surface concentrations of the additives. The reactor is a reactor which we borrowed for the purpose of this project from the process group in Twente. Is one that that Westerterp had used for some work that he did on a trickle flow reactor, or the modeling for that. And it's a high pressure system. We've used it at pressures running between 30 and 70 bar, 3 and 7 megapascals. We've used the temperature range 240 to 300 degrees centigrade. We've used a flow rate that gives a residence time of about a second in the reactor, and 1 gram of catalyst is the normal charge that we use. And we've looked at a variety of different hydrogen to carbon monoxide ratios. For this particular work, it's been mostly kept, I think, at a value of 2, but for some of the other work that we did, we varied it quite considerably. Now, the normal gas dosing system, we have a bypass around the reactor so that we can monitor the composition of the gas phase before it hits the catalyst, and then through the reactor, which is a stainless steel reactor of the normal sort of design, reduction valves, and then GC analysis of our products. So nothing spectacular there that is different to anyone else, but it wasn't very usual for our types of measurement to be working at high pressure, so it was a complete new learning curve for us as far as that was concerned. This shows the behavior, the selectivity of the catalysts containing, in this case, manganese oxide, with as a function of the manganese oxide content. This is a co-precipitated material, I think, and you can see the various products that are formed. This is the untreated material. On the left-hand side, 0 manganese content, so that's the behavior of the normal catalyst. Now remember that the feed does not contain CO2, and hence even with the catalyst, without any additive, we are actually getting some ethanol here, and we're getting also some isobutanol. These seem to be the main oxygen-containing products, and of course with methanol here. And I should stress that the methanol curve here has been divided by 10 to bring it onto the scale, so that the selectivity is predominantly towards methanol. When we add the additive, the manganese oxide, to the catalyst, you'll see that the isobutanol goes up slightly with manganese content. The ethanol content comes down, and the methanol content goes up, so that we have actually had some quite considerable effect on the selectivity of the catalyst. There are other products, and these are predominantly CO2 and methane, and here you can see the effect of the manganese content on those two products. The CO2 is decreased considerably by the addition of the manganese, and the methane content comes up slightly. And we'll be paying some attention to the concentrations of methane and CO2 in what I'll be saying from here on in. These are the results for, I think, for the impregnated catalyst. And here we have it's the same catalyst as we had before, but just showing the effect of temperature. This is the manganese content. These are the results we saw before for the isobutanol, slight increase with increasing manganese content. But here, at this particular temperature at 300 degrees, raising the temperature slightly then gives a significant increase in the amount of isobutanol. Now you can see that this is becoming quite a significant quantity and quite useful for the types of purpose that we had set out. We're doing most of the work at 280 because the kinetics are easier to follow at 280, but obviously if one wanted to use this in practice, one could operate the catalyst at a slightly higher temperature and hope to get considerable quantities of the isobutanol. Now these are the results for an impregnated catalyst, and they compare reasonably favorably with the results that we got with the co-precipitated material. And this shows, again, the effect of different manganese contents. You can see here that with a small amount of manganese, the methanol concentration has dropped off slightly, comes back up again with a higher manganese content. The ethanol doesn't vary very much with the manganese concentration, and again, the isobutanol increases with an increase in the manganese content. This again, as I say, is at 280 degrees. At 300 degrees, we would expect a higher increase here. Now you can see that there is in fact a slight decrease in the methane concentration here, not particularly significant, but a slight decrease. And here we're getting an increase of the CO2 concentration. And the activity of the catalyst is hardly changed by the addition of the manganese. Here are some results now for cerium addition. And here, in this particular case, again, we have the same set of results for the copper zinc oxide alumina for comparative purposes. And you can see that with 2% cerium, we are in fact getting a very significant increase in the isobutanol concentration, even at 280 degrees centigrade. If we go further in cerium concentration, the amount of isobutanol decreases once more. So there appears to be an optimum in the cerium concentration. The methane is kept constant until here, and what in fact seems to be happening is that at high cerium concentrations, we're beginning to get hydrocarbon formation, in other words methane formation, and we're also getting considerably more CO2 in the reaction. We're also getting, and this is significant, a considerable decrease, a significant decrease at least compared to these other two figures in the activity per mole of catalyst per R. Sorry, micromoles per gram of catalyst per R. Now, here are some results fairly typical of the sort of things that we were able to measure, the behavior as a function of time on stream. And this is for this high weight percent of cerium. You can see that the catalyst at this particular set of conditions deactivates considerably. Initially, the methanol concentration goes up, and then it decreases. Well, that's perhaps wishful thinking that it goes up. It's roughly constant then, I should say, and then begins to decrease with increasing time on stream. The dimethyl ether, which is formed initially, disappears completely. Methyl formate was formed in the early stages of the reaction, disappears completely. And the isobutanol also seems to go down very significantly, and in fact after a period of time is no longer there. And this catalyst appears to deactivate quite significantly then as far as the byproducts are concerned. It's not quite so serious with the other cerium contents, but that was an extreme example of the deactivation, the loss of the isobutanol concentration. The other products also change with time a little bit, but much less significantly. Here is the CO2 concentration. It's remarkably constant over that time on stream. The ethane, there's a small amount of ethane being formed. It remains fairly constant, rises very, very slightly. And the amount of methane, again, rises very slightly. But there's not the same significant change in the concentrations. So our indications from those results are that the CO2 and methane are being formed by some different route, are being affected differently by the change in the surface concentrations. Here are two results for the cerium-containing catalyst, co-precipitated, the effect of the pre-treatment of the catalyst. This is a fairly mild pre-treatment in both cases. Here is a result for the 2% cerium material, reduced in carbon monoxide and hydrogen. And you can see that the methanol, ethanol, and isobutanol concentrations are, these two concentrations are reasonably high. The higher alcohol concentrations are quite high with that particular catalyst. And here, the methane is, again, reasonably significant. And the same applies in this particular case. If this catalyst is not treated at high temperature, up to plus, then we are in fact getting quite a lot of isobutanol and ethanol. It's the high temperature treatment of that particular catalyst then decreases these two materials quite considerably. So the catalyst doesn't appear to be terribly stable. The methane concentration, again, is reasonably similar to the concentration that we had with the other catalysts. Now with an impregnated catalyst, here are our results for 3 different cerium concentrations. And compared with the last slide, or the last 2 slides, the concentrations of ethanol and isobutanol are quite a lot lower. And the concentrations of methane and CO2 are considerably higher than they were in the previous ones. You have to take my word for it, because I don't think we've got time to put the other slides back to show you that. The activities are relatively constant. So what in fact seems to happen is that with the impregnated materials, we're getting a selectivity more towards these 2 products, and in the case of these products, they're slightly lower than in the co-precipitated materials. Now, these results tie in reasonably well with the analytical results. First of all, with the XRD results, we find that with co-precipitation, the addition of cerium has no effect on the structure of the catalyst, whereas with the addition of manganese, at greater than about 4 atomic percent of manganese, we find the separate phase, which is probably Mn2O3. It is not terribly clear from the analysis which phase of manganese oxide it is. With with the surface area measurements to begin with, the surface area seems to be relatively constant in the range 23 to 28 square meters of copper per gram of catalyst. There doesn't appear to be any great effect of the cerium and the manganese concentrations. However, that is for the co-precipitates. However, when we look at the impregnated material, the surface area is decreased quite significantly in both cases, by up to about 20%, so that it would appear that the additives, when you put them in by impregnation, are actually decreasing the metal surface area of the resultant catalyst. Now here are some XPS results for the catalysts. These are cerium prepared by co-precipitation. Here are the different cerium contents, and here is, in fact, for comparison, cerium oxide. The spectrum here has been reduced considerably to fit it on the same scale. The peaks are much, much higher than they are for the various copper catalysts. But you can see that at least from 4% upwards, we are getting peaks which are characteristic of cerium oxide. So there does, in fact, appear to be cerium oxide on the surface of the catalyst. CeO2 is segregating, even though it's not visible by X-ray diffraction. And it would appear that that is, in fact, one of the reasons that we're getting different behaviors with time, with the cerium catalyst. We are getting surface segregation of the catalyst, of the cerium to the catalyst surface. Here are some data for the integration of the XPS peaks for various different catalysts. And again, without going into a great deal of detail, it's significant to look at the behavior of these 2 used catalysts, the catalysts after use in the reaction, and we can see that the cerium to zinc ratio, the cerium to copper ratio are both much higher than the catalysts down here, which are fresh materials. And in fact, a 2 mole % used catalyst has a surface ratio there of 1.82, which is in this sort of region for the co-precipitated materials. In other words, something with 2% has a surface concentration which is not all that far away from, let's say, 6 mole % when it's prepared homogeneously. So there is, in fact, quite a clear evidence for surface segregation of the cerium in these used catalysts. But it would appear also that the effect is the same for both the copper cerium ratios and the the zinc cerium ratios, that the amount of cerium seems to go on to both the zinc and the copper, having an effect on both of these. This ratio, the copper to the zinc ratio, remains relatively constant, implying then that the cerium is sitting on both types of site. Now, again, that's rather speculative. I don't think we have enough results to prove that entirely, but it is an indication that that's the way things are working. Now, our results, we think, fit in with a scheme which can be depicted in this sort of way, that the CO and hydrogen are forming some sort of methanol precursor, possibly a formate species, that they then, that forms ethanol, and then goes on to isopropanol and so forth. The methanol is formed directly from that precursor, and it would appear also that CO2 and alkanes are being formed from that precursor. Now, the argument in the literature, at least, is that to go from here towards the higher alcohols, you need a positive ion on the surface of the catalyst. There are two mechanisms in the literature which point in this sort of direction. The first of these two mechanisms is the mechanism given by Mezenek and his colleagues. And you can see that there's a positive ion species. Carbon monoxide insertion occurs in that species, and then you form a longer chain in that way, going from the enolate then to the isobutanol product. The other mechanism, which is suggested by Noonan and his colleagues, is shown here. It's a slightly different insertion mechanism involving an aldehyde insertion, but in both cases they do require a positive ion species in the surface, and our argument is that if we have the right sort of environment, when we add the cerium or the manganese, it can in fact encourage the formation of the higher alcohols. Now let me come up with some conclusions. Some small quantities of cerium and manganese are probably present throughout the catalyst. In other words, by co-precipitation, we get them all the way through the catalyst. When we use impregnation, they will be almost entirely present at the catalyst surface. When we have manganese ions in the material, we get an increase in the fractions of methanol and higher alcohols, and the location appears to be unimportant. It doesn't really make much difference as to whether or not we have got a co-precipitate or an impregnated material. It doesn't have a great deal of effect. In the case of cerium, on the other hand, we appear to get an increase in the selectivity to isobutanol, but the presence of cerium ions at the surface enhances the formation of alkanes and CO2. And then, on the final transparency, the cerium does unfortunately segregate at the catalyst surface under reaction conditions, and the catalyst is therefore rather unstable. And we suggest that there may be some evidence from our results that the alkanes are formed by a different reaction route and require different types of surface sites than the sites that are required for the alcohol formation. And finally, again, we speculate that it may be the positive ions which are on the presence of on the catalyst surface which are responsible for the higher alcohol production. So that's my talk. Thank you very much.
Yes, I assume that you, as other investigators of high alcohol synthesis, have found most of the organic chemistry in the product, and not only ethanol and isobutanol, as you showed in your tables, because well,
we have smaller quantities for the other things, yes, but these are the
including
predominant
aldehydes, acids, and esters.
small quantities, not very large quantities, but small quantities.
What about propanol?
Significantly smaller. This catalyst does seem to give predominance of isobutanol.
So you mean that perhaps you're going directly from ethanol to isobutanol?
Well, there is ethanol present, but there doesn't appear to be propanol, so very much propanol. So yes, indeed, we are suggesting that there is some route. We have no evidence for what that route might be, but this catalyst has significantly higher selectivity than most described in the literature for the acid.
The other point I was to make was that if you start forming higher alcohol and have a syngas with no carbon dioxide in it, it's not surprising that your methanol rate increases because
as you form CO2, yes,
yeah,
it's helping, yes,
yeah.
indeed. Well, I'm sure that's happening, but we are getting quite significant quantities of CO2 gradually as the reaction proceeds.
What sort of conversion are you on in these experiments?
I think they're about 10%, something like that.
It seems that the deactivation of the effect to make more butanol is an important problem, and your explanation for that is that you're surface segregating the cerium, but you need the cerium at the surface to get the effect, and it seems like if you just started out with glass, that you would end up with just the right amount of.
Oh, I think so. That was a particularly bad example of the deactivation of the catalyst. Most of them would operate reasonably well, the lower concentrations, but I showed that slide just to show
I think with
how
a
badly
real
it
low
does.
concentration, you might actually get an enhancement of the effect as it's surface segregated. Did
Yeah,
you ever
no.
see that if you're-
What I think one would conclude is that if you had time to optimize, and we hadn't time to go on and optimize the behavior, a low concentration of cerium at exactly the optimum level would not segregate anymore and would continue to give you the high isobutanol concentrations. So the coprecipitate was fine if you had low concentrations, but it did surface segregate. It's probably the easiest way of making the catalyst is to coprecipitate. You can do it very, very reproducibly, but then you would probably aim for a 0.2, 0.3% cerium in the catalyst. We didn't actually do that.
One more question.
Could I continue a little with this CC bond formation? You mentioned the CO insertion. Could be one possibility. Normally this is true in complexes and then maybe on metal sides more or less. Then the other thing is the aldehyde insertion. Is this identical with the aldol reaction, condensation mechanism, which one earlier discussed in literature? Eliminating water between the two species and then having the new CC bond because of the activated hydrogen, yes, which is easily removed, or something like that.
Well, I think that
which
it
would explain then the branching, the isobutanol.
it's
to be
very,
formed.
very, very dangerous to speculate on the mechanism for the sort of results that
When
we
you
had.
started, so I'm insisting.
Well, I don't honestly think we've got any evidence for it. I think the only reason that I put up the mechanism was to show that in both cases, both of the speculations from the literature do require the surface positive ion, and we were suggesting that the positive ion was actually helping. These types of results are very, very tricky to get at high pressures, and I think that it's dangerous to try and draw these conclusions without tracer studies and things like that as well.
Okay, there's a pressing question.
No, I just want to emphasize that when we did these sort of experiments, also some years ago, we carefully analyzed all the spectrum of aldehydes, acetones, esters, and so on. And it seems that we, as in fission frogs, had equilibrium between the various species within the carbon number. So these should be present, and which one are going to go into the carbon bond formation, we don't know, but the possibilities are there.
Yeah.
Okay, thank you very much. The next paper this morning is titled Methanol Synthesis on Calcium